Welcome back to ME 760 Engineering Analysis 1. So today I want to close out with the series solution for the ordinary differential equation, and there is a handout online for written by Professor Ken Schultz in the Mechanical and the Nuclear Engineering Department here at our university, who taught this class for a long time. The handout is a summary of the series solution and also some important second order differential equations. The other one, and it is online, the other one is continuous operators. And those two handouts are there online. So today I will not go in details of his first part, which is some important second order ordinary differential equations. This is the basis of the special function. So if all of you, I think, are graduate students and you are interested in studying some of the special functions, those special functions are just the solution, series solution of some ordinary differential equation, second order ordinary differential equations, and they are giving the names of the guys who solved those second order linear differential equations with variable coefficients in the 16th, 17th, and 19th century. And usually they solve them using the series solution, Frobenius solution, for example, or the other solution, and they figure out what are the properties of those special functions. So I will just start by giving a brief summary of what we did so far in solving the series solution. So let me check that everything is okay here. Okay. So as you see here, guys, you will notice that the general form is just the y double prime of x plus p of x, y prime of x plus q of x equal to 0. And as you see here, we have two situations. The first situation is when the x naught equals 0, for example, is an ordinary point. So usually we seek a series solution about the point x naught, where x naught is taken to be 0 without loss of generality. So if the expansion is not around x naught equal to 0, so we will change variable and we will make x prime equal to x minus x naught, and now the expansion will be around the point x naught prime equal to 0. So we have two situations. The first case, or two cases. The first case is when x naught is just an ordinary point, so it's not singularity. So in this case we will represent or seek a solution in the form y of x equal to the summation from n equals 0 to infinity for a n x to the power of n, where the initial or the first coefficient a0 does not equal to 0. And in this case we will take this representation or this form of y of x, go back and substitute in equation 1, and we will collect the terms with the same power of x, and we will obtain this form, which is a summation from n equal to 0 to infinity for bn x to the power of n, where bn now is a function of an minus 1, an minus 2, and so on. So we will set bn equal to 0 because this is just a summation of some coefficient multiplied by x to the power of n. If x is not equal to 0, so this means that the bn should equal to 0. So equating bn equal to 0, you will obtain the recurrence relation that will govern the relation between, let's say, an and an minus 1, an plus 2, and an, and so on. So it's a recurrence relation that we will solve and obtain, for example, the even number coefficients like a2, a4, a6, a8, and so on in terms of the a0, and also we will obtain the a3, a5, a7, a9, which are the odd number coefficients in terms of a1. So this is usually the way we solve the problem when we have ordinary points. When the point of interest it's not ordinary, let's say at x naught equal to 0, it's not ordinary, so we have to figure out whether it is essential singularity or a regular singularity. So if x naught is a regular, just regular singularity, Again, we will seek the same expansion for y of x, but now we will introduce another term, which is just x to the power of r. So y now is a function of x and also a function of r, and it is equal to x to the power of r multiplied by this summation. And also we will assume that a naught is not equal to 0 again. We'll take this form and then return back, substitute in equation number 1. Then we will obtain the indicial equation where you will set up x equal to 0, and you will notice that all the terms but or except the first term, which is x to the power of 0, which is the constant now, should vanish, and the multiplication or the equation multiplied by a naught is equal to 0. We assume that a naught does not equal to 0, so for this case, if a naught does not equal to 0, we will obtain an indicial equation that we will solve and obtain R1 and R2. And we stated that we have 3 different cases. The first case when R1 does not equal to R2, and the difference between R1 minus R2 is not equal to what? Is not equal to integer. So we will obtain 2 linearly independent solutions, y1 of x and R1 and y2 of x and R2. What if R1 and R2 are equal? So in this case we have to figure out, we will only be able to obtain one of the solution, but we have to figure out the second one, the second solution. And we note that there are 2 methods in order to obtain the second solution. The first method is the Wronskian method, and the second method is what? The derivative method, which is involved here in the last problem in homework number 7. So the derivative method will depend on whether R1 equal to R2 or R1 does not equal to R2, but the difference is integer. So if R1 equal to R2, we notice that just simply you will differentiate y as with respect to r, and then get the evaluation of this d by dr at R1, and this should be what? Should be your second solution. But what if the 2 roots R1 and R2, they are not equal, but they differ by an integer? So in this case we discover that the derivative of the function y evaluated at R1 will not give you a second unique solution. So we have to multiply by r minus R2, if you remember guys from last lecture, and then differentiate, and this is what you see here. So we have to differentiate the multiplication of r minus R2 multiplied by the y of x and r, instead of just differentiating the y of x and r. So we have 3 different and unique cases. So this is just a reminder of what we did last time. So if you look here for the hands-out online written by Professor Schultz, you will notice that we have several of those series solutions. So we already studied the Legendre equation, and we knew that the Legendre equation has this mathematical form. I'm not going to go in details about the mathematical form here. We knew that this equation has a singularity around x is equal to plus or minus 1 and also infinity. We seek the solution last time around x equal to 0, and the range of the solution, or the solution was valid on the range that the amplitude of x is less than 1, which is equivalent to x is greater than -1 and less than 1. And in this case we obtain the Legendre function of the first kind, as you see it here. We stated clearly last time that if the L is an integer, this infinite series will truncate, if you remember guys, and with the x to the power of 0, or x0 here term, if L is integer. And also we find the second independent solution, and we call it Q here. And we knew that the solution, the general solution for this Legendre equation is just y of x is equal to a multiplied by p, L of x plus some constant b multiplied by q L of x. So those are the two types of Legendre equations. Then there is the other one is the associated Legendre equation, and the difference between the Legendre equation here that you see and the associated Legendre equation is you have an extra term here that has m square over 1 minus x square, and L and m are integers. So usually in order to solve this equation, again, you have to find the singular points, and those singular points again are around x equal to plus or minus 1 and negative infinity. You will seek the solution around x equal to 0, and of course your range of solution will be valid in the interval x greater than minus 1 and less than 1. And again, we will have the associated Legendre function of the first kind, which is just given by this formula here, which is just the mth derivative of the Legendre function. So the associated Legendre function is just some function raised to the power of m over 2 multiplied by the derivative of the original Legendre function here, as you see it, guys. And the second independent solution again will be just the QLM, and again the final solution will be the combination, linear combination of those two solutions, solution number 1 and solution number 2, which is BLM and QLM. So this is just some definition of the Legendre equation as you see here. Then we will move to the Bessel function. And Bessel function, when you solve some problems in cylindrical geometry, you will usually obtain the Bessel function. And the Bessel function, as you see here, is just x square y double prime plus x y prime plus x square minus nu square multiplied by u of x, where x is greater than 0. And usually this equation has a singularity point at x equal to 0 and an essential singularity at infinity. So one solution is the Bessel function of the first kind. Usually we call it first kind and order nu, and it's given by this series expansion here, as you see. So we usually write it as j sub nu of x equal to the summation from 0 to infinity minus 1 to the power of n. Last time one of your colleagues asked me how we get this representation, like minus 1 to the power of n or minus 1 to the power of n plus 1. So you have to look at the series expansion, let's say first term, second term, third term, and so on, and see how often the negative sign and positive sign is interchanged. Let's assume that if you have first term does not have a negative sign, the second term has a negative sign, and so on. So if your first term does not have a negative sign, this means that your exponent should be odd or even. You should have even exponent because you don't have any negative sign. So in this case you have to start with n plus 1, for example. So because n will be 1, 1 plus 1 is 2. So this is how you figure out whether it is even or odd or some form. And what you see here is just the downstairs is just the gamma function. How many of you guys saw the gamma function before? So the gamma function is just a generalized form of the factorial function. So as you see here, the gamma function is defined as the integral from 0 to infinity e to the power of minus t to the power of nu minus 1 dt. So if you have gamma n, this should be n minus 1. If you have gamma nu, this should be nu minus 1. So we will notice that gamma, if we just did the integration by parts for this equation, when you do the integration by parts for this equation, you will end up figuring out that gamma nu plus 1 is just equal to nu multiplied by gamma nu. So for a generalized factorial function, which is the gamma function, you will notice that gamma of 1, if you just substitute here t to the power of what? Nu minus 1, and nu is what? Nu is 1. E to the power of 0 is what? T to the power of 0 is what? 1. And this will be just e to the power of minus t dt from 0 to infinity. If you do the integration, you will notice that this integration is equal to 1. So gamma 1 is just 1. gamma 2, if you substitute here, what's 2 now? So nu is 2 multiplied by, so nu is 1, sorry. So this would be 1 plus 1 is 2. Gamma 2 is equal to 1 multiplied by gamma 1. So this would be gamma 1. Gamma 2 is equal to 2 multiplied by, I think I made a mistake. I think there should be something like plus 1 here. So this is 2 multiplied by gamma 1, and gamma 3 is 3 multiplied by gamma 2, and so on. And the general form, you will notice that gamma n is equal to n multiplied by gamma n minus 1. Okay, guys? And this is what? The factorial of n, because if you remove gamma n minus 1, you will put n minus 1 multiplied by gamma n minus 2. And then remove gamma n minus 2, it will be n minus 2, gamma n minus 3, and so on until you reach to 2, 3 multiplied by 3 multiplied by 2 multiplied by 1, which is just the factorial of n. If you plot just the gamma function here as a function of nu, you will notice that in the positive integer part here, you will notice that you will have a continuous figure like this. And let's say for a integer value 1 and 2, you will have this behavior for the gamma function. For the negative values for nu, you will have some graphical representation for gamma function like this. So this is just a generalization of the factorial. Usually the factorial is defined for a positive value for the number. Let's say factorial 5, factorial 10, factorial 11, and so on. But the gamma function, it's a generalization. So you can have a fraction or an integer number for the definition here. So the Bessel function, again, the solution for the Bessel function will involve in the denominator a gamma of nu plus n, and the nu here is not, if nu is not an integer, the second independent solution for the Bessel function will be j minus nu of x, and we have to linearly combine the first solution and the second solution, and we will obtain y of x equal to a multiplied by the j sub nu of x plus some constant b multiplied by j sub nu x. And both a and b are arbitrary constant that you have to define those constants using the boundary conditions, for example, for the problem in hand that you are solving. So if nu is m equal to m and it is an integer, for example, so in this case the Bessel function is given by j minus m of x, and it's given by this formula here, minus 1 to the power of m gm of x here, if you replace m and minus m. So this is a second independent solution is needed, and the second independent solution is given by what we call Newman function, or the Bessel function of the second kind of order nu, and it is given by this this functional form here, which involve the multiplication of the Bessel function of the first kind multiplied by some cosine function subtracted with j minus nu and divided by sine of theta. So if nu now goes to m, an integer, this is the general representation here, and you will notice that the general representation, it will be a series solution y sub m, and y sub m will have some constant like the mathematical constants that we knew, that by and e and all those mathematical functions. This function here is called the Euler constant. It's given by just 0.57722 and so on. So again, if we have instead of the Bessel function, we have here a plus sign. So if we have a minus sign instead, this will define the modified Bessel function. So instead, if you are confused, you have to go back to this hands out and look for the last term that contains the y of x, whether it is positive or negative. If it is positive, it will be the Bessel function. If it is negative, it will be the modified Bessel function. And the modified Bessel function also will have two solutions. One is the modified Bessel function of the first kind of order nu, and now is given by I, and the second one will be given by k. So you have j and y and I and k So if for example, you are solving a heat transfer equation in cylindrical geometry, for example, and you will notice that you will have, let's say, the Bessel function, you will have the solution, the two solutions will be given by J and Y, and let's say if you are solving a engineering problem that will involve the modified Bessel function, you should get two linearly independent solutions given by I and K. So usually remember that J is accompanied or associated with Y, and I is associated with what? With K, so that you do not mix the problems here again. One of the special functions of interest also in engineering is the Hermite equation, and this Hermite equation is just defined as y double prime of x minus 2x y prime of x plus 2 alpha y of x equal to 0, and the domain of this equation usually is between x equal to negative infinity and plus infinity, because there is no obvious singularity here at any value except what? Except infinity and negative infinity, because you do not have anything in the denominator in the p of x and q of x, so you do not have any singularity here. So if you here alpha is just any real positive number, and essential singularity exists at infinity. We do not have any well-known singularity at finite values for x. So we will have two independent solutions for this equation. One of them is just given again by this series representation for the parameter alpha that we see in the problem here, and the other one is given by the following equation in page number 4. So again, this is all of this is giving in the handout, so I'm just going through a very brief description of what you have in the handout, so that you will have it and keep it for yourself in future if you are doing your research, for example, in mechanical engineering or any sort of engineering, and you encountered, for example, some mathematical representation of a second order differential equation with variable coefficient, and you want to know what type of function this one, you can look for just the handout to figure out what's this function. Then you can find the general characteristics or general parameters and recurrence relation and all the properties for this function from any book of mathematical, detailed book of mathematical functions. Like there is the Bible in mathematical functions. It's called Handbook of Mathematical Function, but by Abramowitz-Stegen. So it's a very well-known and very old book that has a table, evaluated tables for those special functions, and what are the recurrence relation, what are the, for example, if you are talking about the Bessel function, if you get the J, for example, Bessel function of the first kind of order 0, for example, how you will get the Bessel function of the first kind of order 1 and order 2, and what's the relation between them. If you differentiate one of them, how you will get the other. If you integrate one of them, how you will get the other, and so on. So so now when alpha minus m here is an integer, the summation in y1 will always terminate, and after m over 2 term, and you will get a polynomial, and this is what we call Hermite polynomial. So again, like the Legendre formula, we notice that if L is equal to integer, the infinite series will terminate, and we will obtain a polynomial of order L, and this is the Legendre polynomial. So it is exactly the same situation here for the Hermite polynomial. So if the alpha minus m is an integer, in this case you will have a termination for the infinite series, and you will obtain a polynomial, and this polynomial is just the Hermite polynomial. And again, if you search text box about special function, you will be able to figure out, for example, what are the properties of the Hermite polynomial. Again here there is the Legendre equation, and if you look at the Legendre equation here, the general form of the Legendre equation, again, p of x and q of x does not contain any denominator, so again you do not expect that you will have any well-known singularity for finite values of x, so your singularity is at infinity, and usually you define this Hermite equation between x equal to 0 and x equal to infinity, and this equation usually the solution will be given by the series expansion in this form here. And when alpha is an integer, again the summation will truncate after m terms, and this will give what we call the Legendre polynomial. And again, the Legendre polynomial of order n is here, and you can look at the tables of special function to figure out what are the properties of the Legendre polynomial, and what are the, let's say, the recurrence relation, what's the derivative, integrals, and everything of Legendre polynomial, and what's the relation of Legendre polynomial with the rest of other functions, for example. So the closely related Legendre equation is the associated Legendre equation here, and instead of just having 1 minus x, you will have some value of another number called beta added to 1 minus x. So if you have a beta plus 1 minus x, this is the associated Legendre equation. And again, the associated Legendre polynomial is given by the series expansion here, as you see it here. Again, one of the equation is Jacobi equation. This is the form of the Jacobi equation, and this is the series solution of the Jacobi equation. And then we have also the harmonic oscillator, and we knew what is the harmonic oscillator, of course. It's the second derivative of function equal to negative some constant raised to the second power multiplied by the same function. So let's assume that y double prime equal to negative omega square y. This is a simple harmonic motion, and this is what we call the harmonic oscillator, because the harmonic oscillator is represented by a simple harmonic motion, and this simple harmonic motion, usually the general solution is just a sine the square root of the omega, or in this case the nu, multiplied by x plus b cosine nu x. There is again the Chebyshev equations, which is given here. There is the Guggenbauer equation, and also it is given here in the hands-out. One of the most important special function that you will see in mathematical functions, for example, is the Gauss or the hypergeometric equation. And Gauss was a prolific mathematical scientist or mathematician, and he was able to figure out that if you have an equation in this form, for example, x squared minus x y double prime plus 1 plus alpha plus beta multiplied by x minus gamma, all multiplied by y prime plus alpha beta y of x equal to 0. Again, you will notice that the singularities for those equation will be at x equal to what? X equal to 0 and 1 and infinity, because if you take from here x as a constant, as a factor, you will end up with x minus 1. So you will have x multiplied by x minus 1. You will divide by this value. So your p of x will have in the denominator x multiplied by x minus 1, and the q of x will have x multiplied by x minus 1. So the two singularity points will be x equal to 0 and x equal to 1. So when you will seek a solution, for example, at x equal to 0, and the range of the validity of the solution will be just in the interval from x equal to or greater than negative 1 and less than 1. The equation usually, the general solution will be given by the function called f, and this function will be a function of the constants alpha, beta, gamma, and the variable x. So you have three parameters here, alpha, beta, and gamma. So we knew that what are the parameters for the Legendre equation, for example? Only one parameter L. And for the Bessel function, you have only one parameter nu. But for this function here, the Gauss or hypergeometric equation, you have how many parameters? Alpha, beta, gamma, and then the variable x is the same variable x. The most important part here about the, again, about the this hypergeometric function, f usually is given by this, and for particular choice of the three parameters, alpha, beta, gamma, usually the hypergeometric equation can become, and this is the most important part, if you choose, let's say, alpha, beta, and gamma with some choice, for example, maybe you will turn the hypergeometric or the Gauss equation to the Legendre let's say, Legendre equation, or you will turn it to the Chebyshev or Gegenbauer or any other equation. So it's not surprising that many elementary functions can be written in terms of the hypergeometric function. Some of those examples are given in the last page of this handout. If you will see here, for example, when your logarithmic function, for example, ln 1 plus x, and this logarithmic function can be represented as x multiplied by f of alpha equal to 1, beta equal to 1, and gamma equal to 2, and you replace x with negative x, for example. Again, the tangent, the trigonometric function, the inverse tangent function, 10 minus 1x, is just equal to x multiplied by the hypergeometric function of half and 1 and 3/2 and negative x squared, and so on. You will see here is the cosine, here is the Legendre polynomial, here is the Chebyshev, here is the Jacobi, and this is the complete elliptic integrals, for example, and this is the associated Legendre polynomial. So it's a very important function, the Gauss or the hypergeometric function. Another function here investigated by Kummer, it's called the confluent hypergeometric function or equation, and this the hypergeometric equation again has how many parameters? It has what? B and A, and usually this equation again has a regular singularity at x equal to 0 and essential singularity at x equal to infinity, and one known solution for this confluent hypergeometric function or the Kramer function is given just by the equation that you see here, y of x equal to m of a and b, and x just two parameter a and b. So the second independent solution is given by this, and usually the standard form of the second solution is a linear combination of y1 and y2, and namely is given by this. So the confluent hypergeometric function can become a wide variety of function also with particular choices of the parameter a and b. For example, if you want to represent the exponential function, for example, the exponential function is just m of a, and x. So in this case you choose the parameter b equal to the parameter a. So if you have a and b are equal, so you will end up with the definition of the exponential function. This is the exponential integral function. For example, when you choose a and b equal to 1 and you multiply by e to the power of minus x, you have the error function, you have the incomplete gamma function, the Bessel, the modified Bessel, the Hermite polynomial, the Hermite polynomial again, and Legendre polynomial. So just download this very interesting handout that contains all the special function of interest in engineering. So again, most probably I will not bring this stuff in the exam, but it will be of interest to you guys to keep it, because I knew that all of you are graduate students, and it will be of interest to you, especially if you are doing any type of mathematical analysis for your experiments, or if you are doing computational work or whatever. So now we will start a new topic, completely new topic, and this is the continuous operator. And again, we have the hands out for this continuous operators online that Professor Schultz wrote himself. So instead of taking notes, you can just download this one and stitch it to your notebook, for example, and just continue what I'm doing on the blackboard. It's better not to take notes, because this is a complete lectures given by Professor Ken Schultz. Again, this is also on the hands out folder online. So let's start the definition of linear operator here. So linear operator. So we will define first what we mean by a continuous operator. And usually we will call it, as we talked before, O. So this is not theta, this is O. It's an operator if you operate over a function f of x you will obtain another function g of x, and it's just, when you do this, it's just a mapping. So if you have a domain here, but you have a function of x is defined over this domain, and you have another domain where a function g of x is defined over another domain here, and you operate the operator O over the f of x here, you will just map some point from this domain to this domain. So this is just using the operator O. So it's to maps a function into another function and the operator usually will be linear if the operator O will operate over a function f of x plus another function g of x, and you obtain same operator will operate individually over the first function f of x plus the same operator operated over the second function g of x. So this is called a linear operator. So can you give me an example of linear operator? Yeah, derivative. So examples of linear operators will be the derivative. So if you have O is equal just to d by dx, and it is linear because if you just differentiate two functions added together like f of x and g of x, it will be the differentiation of the first function plus the differentiation of the second function. Again, operator can be the derivative to the power of n, is exactly the same, or the operator will be the integral from, let's say, a to b or whatever for some function a to the power of alpha x plus beta x dx, for example, something like this. So this is the definition of the linear operator. So we have to define the inner product for the operators, and usually this definition is given by if you assign a number to a pair of functions. So the definition is, let's say that you have the inner product of function f and g, and this is defined as the integration from a to b in certain interval for the complex conjugate of a function f. So we will assume from now on that our function is a general function. It's not a real function, so it might be a complex function. So this is the f star of x multiplied by j of x dx, where just the integration from a to b will be just the range of this function, and what you see here as a star is just the complex conjugate. So again, the properties of this continuous operator and the inner product is just as the properties that we discussed before in the linear algebra and linear vector spaces. So if you have some constant alpha multiplied by the function f inner product with the function g, it will be just alpha multiplied by the inner product of the function f and g. Second property is if you have f inner product with alpha j, where alpha is constant, again will be alpha multiplied by f and g again. And the third property is just if you have F inner product with alpha 1, a linear combination of alpha 1 and alpha 2, and G1 and G2. So you have alpha 1 G1, alpha 2 G2. This will give you just alpha for F and G1 plus alpha multiplied by F and G2. So this is alpha 1 and alpha 2, for example. Then we can move on and define the adjoint of a linear operator. The adjoint of the linear operator. So if we let O to be a real continuous operator, operating on L2 integrable function, and we'll define what we mean by L2 integrable function in a minute. F of x such that O is operated over F. We will have is another function of x. So O dagger is the adjoint of the operator O if we have the following relation satisfied. And this relation is just if you have a J dagger, a function here, adjoint function, and you have the operator operated over the function F will be equal to the adjoint operator operated over the adjoint function G and inner product with the function F. So if you have a function G inner product with operator O operated over the function F equal to the adjoint of this operator operated over J dagger and inner product with F. So in this case this is a adjoint operator. So where J adjoint here R is also is L2 integrable function of x, and often with different properties. So usually the function is called L2 integrable function. So L2 integrable, and usually it is defined as if you have two functions, one function, the inner product of one function with itself. If you remember, x dot x will give you what? X squared. So what if the function is a complex function? This is the definition for this inner product, just a to b multiplied by f of x dx. what's the, if you multiply a function by its complex conjugate? It's a squared and it's a real number. Yes? It's a squared and it's a real number. Yes? If you have a plus bi and a minus bi, if you multiply both of them, you will have what? A squared plus b squared, and this is just a real number. Yes? So if this inner product of a function with itself is less than infinity, so in this case we call this L2 squared integrable function. Can you give me an example of a function that's not L2 integrable function? A constant, if you try to integrate a constant from 0, a is 0 and b is infinity, will give you what? Infinity. So it will not satisfy this condition. Did you understand? Did you understand? So now let's take an example to just simplify this idea here of the linear operators. So let this linear operator O is equal to d by dx. It's just the derivative operator, the first derivative operator, and it is defined in a region between A and B, where both f and j dagger are real functions, and they are vanishing at A and B. So those, how many functions I will have between A and B? I have two limits, A and B. How many functions you can plot between A and B? You can plot a function like this, you can plot a function like this, you can plot a function like this. So you have infinite number of functions. We do not restrict ourselves to any specific function. So in this case, if you just write the definition for the adjoint operator, so you have the function j dagger inner product with the operator O operating over the function f, and this is given by what? A to b j dagger of x multiplied by O from the definition. I think it was just there. Maybe did we define? I think I defined I defined it in the first page. Maybe we'll return back and define it here. So it is, this definition here is just from A to B j dagger star multiplied by the operator operated over the function f of x dx, and this is equal to this is equal to A to B again the operator operated over the function j multiplied by f of x. So again, this is the function g, and as you see here, the star will go away because this is a real function. So for a real function, the complex conjugate of the function is the same function. So this is j dagger here, okay, multiplied by the operator O operated over the function f. What's the operator O in this case? D by dx operated over the function f dx. Okay guys, so what will happen now is we will do the integration by part, so that we try to get the second lower part of the integration over there that you see here. So when we will do the integration by part, we will reach to the following representation. This will give us g of x dagger multiplied by f of x from a to b minus the integration from a to b to dg of x by dx multiplied by f of x dx. What's this? F and g, they vanish at the borders. So this should be equal to what? 0. And if you just look at this part here and this part here, so compare. You have f of x and you have f of x. And then you have some operator which is the adjoint operator operated over j dagger. What's this? You will notice that the operator adjoint operated over j dagger, which is over there. J dagger is just equal to d by dx minus d by dx multiplied by j dagger of x. So what's the operator, the adjoint operator now? So this will lead you that the operator, the dagger operator, is just negative d by d what? D by dx. So when you have the first derivative, the adjoint of the first derivative will be what? The negative of the what? Negative of the operator. Next time I will show you that if we take the second derivative, the operator, the adjoint operator, will be the same as what? As the operator itself. So this is called self-adjoint operator or Hermitian operator. It's like the Hermitian function. So I will show it to you next time, and then we will go into the details of the properties of those operators. Do you have any questions so far? Okay, thank you so much.